Hi, everyone. Brittany is a third-year graduate student in the Pribram-Jones group at UC Merced, and she earned her bachelor at UC Santa Barbara, where her research with the Moscowitz group focused mostly on the physics and chemistry that arises from nanosystems. Before undertaking her doctoral studies, she worked with analytical method at a lab technician for industrial oil analysis company. And at the moment, her current research interests include studying finite temperature DFT and work-dense matter systems. Some of her favorite activities outside of work include hiking, paddleboarding, giving back to the community through volunteer programs that work for underprivileged children and their families. And the stage is yours.
Thank you, Juri. Okay, so hello, everyone. Thank you so much for joining me. Today, I would like to discuss adiabatic connection approaches to thermal density functional theory. And thermal DFT is important in studying high energy density science, which is a vast field that encompasses enormous ranges of temperatures, pressures, and densities. And more recently, interest has stemmed down to warm dense matter, which is a highly energetic phase of matter characterized by strongly correlated electrons, quantum effects of electrons, and thermal effects. And this phase of matter tends to be found within planetary cores and in white dwarf atmospheres. And a better understanding of warm dense matter can help us gain insight and better understand and model fusion energy experiments, such as those conducted at the National Ignition Facility at Lawrence Livermore National Laboratory and on the Z machine at Sandia. Now, modern day DFT employs the Kohn-Sham method, which expresses the ground state electronic energy in terms of the following quantities, where this final quantity is the large part of focus in developing DFT. Sorry, I'm just trying to get all the windows out of the way. Well, it turns out the adiabatic connection gives us an exact expression for the exchange correlation energy, the ground state exchange correlation, that is, as a solely potential contribution at the expense of having to evaluate at all intermediate lambda. However, this expense provides us with one of the most useful tools for analyzing density functionals. So by integrating over the coupling constant lambda from 0 to 1, we are effectively connecting this fictitious Kohn-Sham reference system of non-interacting electrons at lambda equals 0 to the physical system at lambda equal 1. And so this schematic here shown on the right, which is kind of what we would expect the ground state adiabatic connection to look like, conveniently shows us the components of the exchange correlation energy. And we can also extract things like the kinetic correlation, which is the difference between the kinetic energy of the exact system and the kinetic energy of the Kohn-Sham system. Now, we can introduce temperature into our system by expressing our system in terms of the free energy, and rewriting in terms of the Kohn-Sham quantities. We can get AXC, our component of the exchange correlation free energy. And we can draw a general schematic of what we think the finite temperature adiabatic connection would look like. And we see that our energies are now expressed as free energies, and we now have entropic contributions. So we have the kentropic correlation rather than the kinetic correlation. And we can see that the behavior of the exchange free energy is predictable with temperature, whereas the behavior of the correlation free energy is not so predictable with temperature. It's a little more complex, or a lot more complex. One of the tools I use to generate finite temperature adiabatic connection curves is something called simulated interaction strength scaling. So we can first extract the exchange free energy by taking the high density limit of the exchange correlation free energy, where the lowercase a denotes the exchange free energy per particle. Next, we can use a convenient relationship between the lambda scaled correlation free energy and the correlation free energy in terms of the scaled, or the coordinate scale density. So using this and keeping in mind that lambda is equal to the reciprocal of gamma, so lambda goes to 1 over gamma, we can extract the correlation potential and finally obtain an expression for the exchange correlation free energy, or the finite temperature adiabatic connection. Using this along with a respected parameterization of the exchange correlation free energy for the uniform electron gas at warm dense matter conditions, provided by Groth and collaborators, I was able to generate some finite temperature adiabatic connection curves. So generating these using the parameters RS and tau, where RS is related to density, so it is inversely proportional to density, the Wigner-Seitz radius, and tau is the absolute temperature, which is of the order of 10 to the 6 Kelvin. So it looks pretty nice, it looks well behaved, but what about for another density? So let's try a lower density, which corresponds to a higher Wigner-Seitz radius. And we can still see that it looks like the general schematic shown earlier, but with some distinct differences from the previous plot. So let's look at some of these differences. So first off, we can see that the magnitude of curvature of the correlation part, so the curved part, is much larger for the smaller density on the left than it is for the density on the right. We can also see that on the left, it looks like the curves will diverge if we go beyond the physical interacting strength, whereas for the higher density, the plot on the right, the curves appear to converge if we were to go beyond physical lambda strength. And I also want to clarify that for convenience and just to make things more clear, I've only included the exchange component for the highest temperature, but the other exchanges follow the same trend. So if we trace the curve back to the y-axis, we can plot the exchange. So as the temperature decreases and we go to these lower temperature curves, the exchange also decreases with them. Okay, so that's all well and good, but how can we further validate this method other than just looking at plots and seeing if they look like we expected? Well, the values obtained from the formalism in this work should match or agree with the values from the Groth parameterization. So I was able to obtain values from the Groth parameterization using the Fortran code that they provided. And I was satisfied with the agreement between the values obtained by integrating over the finite temperature adiabatic connection curves. Furthermore, if you increase the resolution on the calculations done with my method, the values agree even more. So the function employed in the Groth parameterization is a Pade function, and this is indeed the AXC employed in this work. And I wanted to focus or put some focus on the electron degeneracy parameter theta. So we can see that the function used here for the exchange correlation free energy is a function of this electron degeneracy parameter, which not only depends on temperature, but as we can see, also depends on density. Well, this is helpful in another way in that we can see that the ground state exchange can be related to the finite temperature exchange via a thermal reduction factor Rx, which is a function of the electron degeneracy parameter theta. And Rx can only depend on the temperature and density through theta, this electron degeneracy parameter. So let's look at how R of theta behaves so we can get a better idea of how this will affect our exchange energies. So we see that at a low electron degeneracy, we simply get 1 for R of theta. So 1 times the ground state exchange, we simply get the ground state exchange. However, as the electron degeneracy increases or theta gets bigger, R of theta gets smaller. So now we have at large theta, we have a very small number multiplying the ground state exchange, giving us a very small number for the finite temperature exchange. So as theta gets larger, R gets smaller, and the finite temperature exchange gets smaller. And the behavior of Rx can be better understood using the basic scaling relationship below of the coordinate scale of the exchange, a function of the exchange of the coordinate scale density with the unscaled coordinate density function. And since the total LDA exchange free energy is equal to the following integral, a thermal LDA exchange free energy density must have the following form, where Fx is equal to the Ax in this work. But since we are employing the uniform electron gas in this method, we simply want the exchange free energy per particle. So we do not integrate, and we end up with a ground state exchange with the following form where D is this constant here. Okay, so we're not taking the integral. Okay, so if our formalism is valid, then recalling the box equation, along with the fact that WXC goes to AX at lambda equals 0, our exchange correlation energy should equal, or WXC should equal AX at lambda equals 0. If we take the ratio of WXC at lambda equals 0 to EX for curves generated with the same theta, then all of these curves should line up at the same point at lambda equals 0. So we can achieve multiple curves with the same electron degeneracy by manipulating tau and RS. So these individual characteristics can be scaled while keeping theta constant. So let's check if the method holds true. Will curves generated with the same electron degeneracy, if we take this ratio of WXC to the ground state exchange, will the curves line up? And sure enough, luckily they do. So this helps further validate our method. And we can see that the exchange increases with increasing electronic degeneracy. But if we zoom out to larger interaction strengths, this reveals to us the complex behavior of the correlation. So we can see that correlation is actually non-monotonic with the electron degeneracy parameter, and curves generated with one electron degeneracy parameter actually overlap with other degeneracy parameter curves. Well, it's helpful that this electron degeneracy parameter is actually related to the Lieb-Oxford bound. So the Lieb-Oxford bound is an inequality that provides us with a universal lower bound to the exchange correlation energy, or the zero temperature exchange correlation energy. And it has been used to successfully constrain some of the most successful approximations to the exchange correlation functional. And we can rewrite this bound in terms of the LDA exchange functional, where it'll have the following form where CLO and ALDA are constants, which give us the value of 2.21. So this is multiplied by the ground state exchange, which, if we recall another expression here in the, we'll see in the next slide. So let's see what we can do with this as kind of a quick, naive approach to investigating the temperature dependence of the Lieb-Oxford bound. So what if we insert or substitute the ground state exchange with the finite temperature exchange energy and see if that provides a bound for this, for the finite temperature exchange correlation energy? So we tried that, and it did not work. Only the original zero temperature Lieb-Oxford bound was successful in constraining all three curves. And we can also see that the temperature adjusted Lieb-Oxford bound does more poorly for higher temperatures than for the lower temperatures. So one step to seeing how we can make some sort of statements or find some sort of inequality that bounds the finite temperature exchange correlation energy, let's look at a situation where the original Lieb-Oxford bound is most likely to hold. So a situation where the exchange free energy will be much lower than the ground state exchange energy, because we know the Lieb-Oxford bound binds the ground state exchange. So an instance where this is likely to hold is when we have large theta. So if we recall, large theta gives us a very small Rx. Small Rx multiplied by the ground state exchange will give us a small finite temperature exchange. So a chart to kind of keep track of the different dominating components that will hopefully help us generate this bound, this finite temperature or temperature adjusted Lieb-Oxford bound is shown below. So again, we can vary the parameters RS and tau while keeping theta constant. So if we recall from from earlier slides, we saw that at the higher RS value, which corresponded to the lower density, we had the correlation component dominating. Whereas at the moderate density corresponding to a low RS value, we had the exchange component dominating. However, when we have both effects high, so to give us a large theta, we make RS and tau high, we have competing temperature and interaction effects. So it's kind of intuitive when we have a high temperature, we expect things to happen with the density, but depending on how high the density is and how high the temperature is, we're going to have competing effects, and it's not so easy to tell which dominates, the exchange or the correlation. Again, for the low RS value corresponding to the moderate density, we recall the exchange dominated, but then we go to this moderate region or this cross region where we have to consider the competing temperature and density effects. And again, it's not so easy to tell which component dominates at zero temperature. So things about the exchange here, then we can hopefully make some sort of statement about the finite temperature or temperature adjusted Lieb-Oxford bound. So this leads to future work. We saw that a simple extension of the finite temperature exchange and the Lieb-Oxford bound didn't hold. We didn't investigate what happens to the constant CLO at finite temperatures. So a next step would be to explore whether or not there exists a universal finite temperature bound on the exchange correlation energy, or exchange correlation free energy. I'd really like to acknowledge outstanding undergraduate Zachary Mowry for his help on this work, Sara Giarusso and Juri Grossi for fruitful conversations on the topic, and of course, my advisor, Professor Aurora Pribram-Jones, the Consortium for High Energy Density Science, and the DOE, or Department of Energy, for funding my work, as well as the Center for Chemical Computation and Theory, at UC Merced, my institution. And I'm very thankful to everyone for their help with this work. So thank you so much.